In last video we discussed about the bond enthalpy, and bond enthalpy, it is the amount of or average amount of energy required to break all the bonds in 1 mole of substance. It is always positive and it is expressed in kilocalorie per mole or kilojoule per mole. Bond enthalpy for diatomic molecule is equal to the energy of atomization or atomization energy for diatomic molecule, and for polyatomic molecule we consider average bond enthalpy. So this part already we discussed in last video. Now next point is average bond enthalpy and heat of formation. So we can calculate heat of formation from the average bond enthalpies of various bonds present in the molecule. Now before that, for different bonds the average bond enthalpies are: for hydrogen, to break bond between two hydrogen atoms, the energy required, it is 436.4 kilojoule per mole. This is the average or bond enthalpy of hydrogen, HH bond. For Cl-Cl bond enthalpy is 242.7 kilojoule per mole. To break bond between two oxygen atoms, it is a double bond. To break double bond, a little bit higher energy is required, and it is 499 kilojoule per mole. Bond enthalpy for CH bond is 416 kilojoule per mole, and for OH bond it is 463.5 kilojoule. So these are the bond enthalpies of most common bonds in organic compounds. Now enthalpy of formation or heat of formation, it is calculated from bond energy of reactants and products, and the formula is enthalpy of formation, it is equal to sum of bond enthalpy of reactants minus sum of bond enthalpy of products. So with this formula, by using this formula, we can calculate the heat of formation of that particular molecule or compound. We take example, calculate the enthalpy of the following reaction, enthalpy of formation of the following reaction, and the reaction is ethylene gas when mixed with hydrogen gas. There is a formation of ethane gas. The bond energies are given for carbon hydrogen, carbon single bond, carbon double bond, and hydrogen bond. Bond energies are given. It is 414, 347, 615, 435 kilojoule per mole respectively. And we are going to find out the enthalpy of formation or heat of formation for ethane. Now enthalpy of reaction or enthalpy of formation, it is equal to total bond energy of reactants minus total bond energy of products. Now the reaction, it can be written as, now here all the bonds are shown separately. Here in reactant there is one carbon double bond. There are 4 CH bonds, 1, 2, 3 and 4. There is one hydrogen bond. In product or in ethane there is one carbon single bond, and there are 6 carbon hydrogen single bonds, 1, 2, 3, 4, 5 and 6. Now the formula is delta H is equal to bond enthalpies, sum of bond enthalpies of reactants minus sum of bond enthalpies of products. Now in reactant there are 4 CH bonds, and therefore delta H is equal to 4 into CH plus there is one carbon double bond, so plus carbon double bond plus bond enthalpy of carbon hydrogen single bond. So there is one hydrogen single bond is there, minus in product there are 6 carbon hydrogen single bonds, so 6 into CH, plus there is 1 carbon carbon single bond. So just to substitute the values of bond enthalpies of each bond, then we get 4 into 414, this is the bond enthalpy of CH bond, plus 615, it is the bond enthalpy of carbon carbon double bond, plus 435, it is a bond enthalpy of hydrogen hydrogen single bond, minus 6 into 414, it is the bond enthalpy of again CH bond, plus 347, this is the bond enthalpy of carbon carbon single bond. Now when we solve this, the answer is minus 125 kilojoule per mole, and this is the heat of reaction or heat of formation of ethane, or heat of formation of ethane is, or enthalpy of formation of ethane. The next point is enthalpy of neutralization. Now enthalpy of neutralization, it is the amount of heat evolved when 1 gram equivalent of an acid is completely neutralized by a base in dilute solution. It is enthalpy change accompanying a neutralization reaction where there is involvement of 1 equivalent of acid and 1 equivalent of base. This is called as enthalpy of neutralization. We'll take example. Suppose strong acid HCl, it is mixed with strong base, that is NaOH. Both are strong electrolytes, and therefore in aqueous solution there is 100% dissociation. We get ions. HCl gives H plus and Cl minus, and NaOH gives Na plus and OH minus. And HCl reacts with NaOH, and there is a formation of NaCl and H2O. NaCl is also strong electrolyte. It undergoes 100% dissociation plus water. So at the time of neutralization reaction or this simple reaction, there is a evolution of heat, that is the enthalpy of neutralization, and it is minus 13.7 kilocalorie. This minus sign indicates heat is evolved. Now when we cancel the common ions Cl, when it is cancelled, similarly when Na plus are cancelled, net reaction is there is a reaction between H plus and OH minus to form undissociated water molecule. So this enthalpy of neutralization for strong acid and strong base, it is nothing but the amount of heat evolved when 1 mole of water is formed from proton and hydroxide ion. For strong acid and strong base, enthalpy of neutralization is always constant. Whichever may be the strong acid and strong base, this value is constant, because net reaction is, it is the reaction between H plus and OH minus to give water, and therefore the enthalpy of neutralization for strong acid and strong base is constant, and the value is minus 13.7 kilocalorie. But for weak acid and weak base, enthalpy of neutralization is less than minus 13.7. It is always less than minus 13.7 kilocalorie. Now from this enthalpy of neutralization of strong acid and strong base or weak acid and weak base, we can find out the enthalpy of dissociation for weak acid and weak base. So next point is enthalpy of dissociation of weak acid and weak base. Weak acid and weak base, they undergo less dissociation in water because these are the weak electrolytes. 100% dissociation is not there. And what is enthalpy of dissociation? Definition is the change in enthalpy when 1 mole of weak acid or weak base is completely dissociated into respective ions. That enthalpy or energy, it is called as enthalpy of dissociation. But already I told you they never undergoes 100% dissociation, and directly we cannot determine the enthalpy of dissociation of weak acid and weak base, but indirectly we can find out. Now consider example, weak base, when, that is ammonium hydroxide, when undergoes 100% dissociation to give NH4 plus and OH minus. Whatever enthalpy change is there, that is the enthalpy of dissociation of ammonium hydroxide, and for ammonium hydroxide it is 1.4 kilocalorie. But as I said, it never undergoes 100% dissociation. So practical determination of enthalpy of dissociation of weak acid or weak base, it is difficult due to their partial dissociation or not 100% dissociation, but indirectly we can find out from the enthalpy of neutralization. And here is the method, the calculation of enthalpy of dissociation of weak base, that is ammonium hydroxide. And the steps involved are, first of all, enthalpy of neutralization of strong base, that is NaOH, and weak base, that is ammonium hydroxide, is experimentally determined. Enthalpy of neutralization of weak base is also determined experimentally. So both are experimentally determined. For example, for strong base, enthalpy of neutralization is minus 13.7 kilocalorie, and for weak base it is minus 12.3 kilocalorie. Now the enthalpy of dissociation of weak base, it is the difference between enthalpy of neutralization of strong base and weak base. So just by taking difference or just by subtracting enthalpy of neutralization of strong base from the value of enthalpy of neutralization of weak base, we get the enthalpy of dissociation of weak base. For example, suppose strong base, that is sodium hydroxide mixed with HCl, there is a formation of NaCl and water. Enthalpy of neutralization is minus 13.7, already I told you. This is equation number 1. Weak base, when mixed with HCl to form ammonium chloride, it is a salt plus water. Enthalpy of neutralization for this weak base, say it is minus 12.3 kilocalorie. Now subtracting equation 1 from equation 2, then we get, so this is the equation number 2, this is equation number 1. So we are going to subtract equation number 1 from equation number 2, and therefore sign of each ion, it is reverse. So this is the minus sign. So first of all we cancel the common ions. So minus sign, minus Cl, Cl minus gets cancelled. Na plus gets cancelled. This Cl minus is cancelled. So minus H plus H plus, these are on same side, they are cancelled. So minus H2O plus H2O, it is also cancelled, and therefore net reaction is ammonium hydroxide combines with, or it gives, not combines, ammonium hydroxide gives NH4 plus OH minus. So already NH4 plus is to the right side, but here OH minus, it is to the left side, but it has a minus sign. When it goes to right side, its sign will be plus. And meaning of this is enthalpy of dissociation of ammonium hydroxide, it is equal to enthalpy of neutralization of weak base, that is ammonium hydroxide, minus enthalpy of neutralization of sodium hydroxide. Now we know these values, value of enthalpy of neutralization of weak base and strong base. So it is equal to minus 12.3 kilocalorie minus 13.7 kilocalorie, and the answer is plus 1.4 kilocalorie. 1.4 kilocalorie. So this is the enthalpy of dissociation of ammonium hydroxide. So here we completed the thermodynamics, chemical thermodynamics.